All right. The fundamental theorem of calculus. Page 282 is where we're going to start. We're going to do a little reading here. It says you've now been introduced to the two major branches of calculus: differential calculus, derivatives, and integral calculus. And remember, we said integral, we use the word indefinite integral, we use the word antiderivative to mean the same thing. So when you see antiderivative compared to derivative, you're kind of figuring they're related, right? I mean, we kind of did our rules backwards to get antiderivatives. But then what you don't know is, why do they call it integral? Because then we then called something else integral. Remember when we found the areas under curves, we called those definite integrals? So why would you use the same word, integral, to talk about adding up areas and to talk about antiderivatives? Getting there. So at this point, these two problems might seem unrelated, but there's a very close connection. The connection was discovered independently by Isaac Newton and Gottfried Leibniz, and is stated in a theorem that is appropriately called the fundamental theorem of calculus. Now, we've all heard of Newton, and he's much more famous for a couple of reasons. One, he did a lot of other stuff besides calculus, right? I mean, science courses could have ended in 6th grade if he'd have never lived, right? Okay? And he spoke English, so we tend to learn him more, all right? So informally, the theorem, they're talking about the fundamental theorem of calculus, states that differentiation and integration are inverse operations, in the same sense that division and multiplication are inverse operations. To see how Newton and Leibniz might have anticipated this relationship, consider the approximations shown in figure 4.27. And so, let's see if I can find my cursor. So we take a look at these. It says the slope of the tangent line was defined using the quotient, change in y divided by change in x, right? y2 minus y1 over x2 minus x1. Then, of course, we had to find the limit as x approached 0, or as delta x approached 0. And then, similarly, the area of a region under a curve was defined using the product, change in y times change in x. Now, we never wrote it that way. We wrote f of x dx, right? Where f of x was the height. But look, if your rectangle is sitting on the x-axis, and then we call the height f of x, but really, wouldn't that be whatever the y-coordinate is minus the y-coordinate of 0? So you can call it the change in y. We never did, but it would have been the same thing. Okay? So, change in y times change in x. So yeah, I mean, that one's set up with division between those two things, this one with multiplication. So there is an inverse operation there, or an inverse relationship going on, because multiplication and division has an inverse relationship. So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to have an inverse relationship in the same sense that division and multiplication are inverse operations. The fundamental theorem of calculus states that the limit process preserves this inverse relationship. So when we find the limits to get the exact slope of the tangent line and the exact area under a curve, you still are doing the inverse operations. Here's what the theorem states. It's at the bottom of 282. It should have its own page. It should be the only thing on the page. It's a big deal. Now, some books will parenthetically call this the evaluation theorem or the calculating theorem, because it tells us how to solve a definite integral and get a number. We don't know how to do that yet. We've set up definite integrals, and we've used geometry to find the definite integral, because the definite integral is defined to be the area under the curve if the curve's above the x-axis. Okay? But now we have a way to use calculus to do that. So if a function f is continuous on the closed interval from a to b, and f, capital F I should say, is an antiderivative of little f, so we're getting back to that notation. Capital F is the antiderivative of regular f on the interval from a to b. Then the definite integral from a to b of f of x dx equals capital F of b minus capital F of A. In other words, the definite integral from A to B equals the antiderivative of f evaluated for the upper limit of integration minus the antiderivative of f evaluated for the lower limit of integration. Anybody see something that might hold us back a bit? Can we find the antiderivative of everything? Yeah, there's a lot of functions we cannot find the antiderivative of. Because it's not the only things we can find the antiderivative of are just using derivative formulas backwards. So there's a lot of things we can't find antiderivatives. Products or quotients, right? There's a lot of things we can't do. So guess what we're going to do this semester? Yeah, we're going to learn how to find the antiderivatives of a lot more types of functions. Okay? All right, so you got to have that committed to memory. It will never go away. All right. Now, some guidelines for using the fundamental theorem of calculus. It says, provided you can find an antiderivative of f, that's a big provided, okay? You now have a way to evaluate a definite integral without having to use the limit of a sum. So, when applying the fundamental theorem of calculus, the following notation is convenient, and in fact, we'll use it. So, the integral from a to b of f of x dx can be written as the antiderivative of f of x, and then this notation right here means evaluated from a to b. So in other words, we'll find the antiderivative, we'll put that little bracket from a to b, so evaluated from a to b, and then that is the antiderivative evaluated for b minus the antiderivative evaluated for a. We'll look at that in a minute if we want to. Maybe we won't. Now, we don't need to use c anymore. Well, I'll take that back. We don't need to use c for a definite integral. We'll still use it for indefinite integrals. But here's why you don't, okay? So if we take the antiderivative of f of x and call it capital F of x, we always put plus c, right? But if we're doing that twice, right, because the capital F of b minus capital F of a, well, wouldn't c distribute the negative minus c just give you a 0? So you don't need to bother writing it down. Okay? All right, let's see how this works out. We're going to have several examples. So turn to page 291. And we'll start with number 3. It says use a graphing utility to graph the integrand, and then use the graph to determine whether the definite integral is positive, negative, or 0. Now, I like the fact they're having us do this because we can't forget what we've been working on, which is the definite integral equals the area under, or I say under a curve. What I really mean is the area between the curve and the x-axis is what I really mean, isn't it? And then remember this, before we graph this, if the entire region is above the x-axis, we'll get a positive area. It's truly the area. If the entire region is below the x-axis, we'll actually get the opposite of the area of that region, won't we? We'll get a negative signed area. We call them signed areas for a reason. A region above the x-axis has a positive signed area. A region below the x-axis has a negative signed area. If there's just as much above and below, then that's when you'll get a definite integral of 0, because the negative signed area and the positive signed area, when you add them together to get the area of the whole region, well, would cancel each other out and give you a 0. So, if there's more of the region above the x-axis, our definite integral will be positive. If there's more of the region below the x-axis, our definite integral will be negative. If there's the same amount above and below, our definite integral will be 0. All right, so let's graph this on our calculator. So that's what it looks like when you graph it on your calculator. What's it look like? Positive, negative, or 0? Yeah, there appears to be, and appears to be is all we can do, isn't it? I mean, we can use our calculator to find the integral. Have I ever shown you how to do that? We'll do that eventually, okay? But it appears that this region right here and this region right here are the same size. Therefore, our definite integral is going to equal 0. Now, this graph was symmetric to the origin. Do you remember what you call that? Odd or even? Odd. So this is an odd function. So it's symmetric with respect to the origin. So be kind of looking for that to happen. What if I change that to be like -4? Well, then it's this, and then we'd get a negative definite integral, wouldn't we? Even functions are symmetric to the y-axis. Odd functions are symmetric to the origin. And that's handy with definite integrals because it's handy. For this. So by looking at the graph, it appears there's the same amount of region above and below the x-axis. But if I recognize this as an odd function, one that's symmetric to the origin, then I know there's the same amount above and below the x-axis. Number 9. Evaluate the definite integral of the algebraic function. Use a graphing utility to verify your result. And I will show you how to do that after we've done this by hand. So here's your first example of how to use the fundamental theorem of calculus to evaluate a definite integral. All right, so we're going to find the integral from -1 to 1 of t squared minus 2 dt. So f of t, they gave us t as a variable instead of x, is t squared minus 2. So the fundamental theorem of calculus tells us to evaluate this by finding the antiderivative of f of t. Well, what's the antiderivative of t squared? Nope, that's the derivative. Yeah, it's the power rule. It's backwards from the power rule for derivatives. It's the power rule for integration. You add 1 to the exponent, make it a 3, then you divide your coefficient by the new exponent. So 1/3 t cubed, or t cubed over 3, as some of you said, minus, and then we can really use the power rule again. That 2 is actually a 2t to the 0, which would be, when you find the antiderivative, that would be a t to the 1, divide your coefficient by that new exponent. So, and it was a negative already, so -2t. Don't need to put plus c, because this is a definite integral. And so then look what I've got here. I've got that new notation. The bracket with a -1 and a 1 means evaluated from -1 to 1. We're at this stage right here. Okay? Now, we're going to this stage. So, the antiderivative that we just found, evaluated for 1, So that's 1/3 times 1 cubed minus 2 times 1 minus the antiderivative that we just found evaluated for -1. Now, be careful with your parentheses. I've got to subtract all of capital F of A. So I got to put what I get in parentheses. So minus parentheses 1/3 times -1 cubed minus 2 times -1. The parentheses are important. Don't leave them off. So evaluating, everybody with me? Now it's arithmetic. Okay? So 1 cubed is 1. 1/3 times 1 is 1/3. -2 times 1 is -2. And I've got the first parentheses almost evaluated. Minus, now I'll work on the second parentheses. When I cube -1, I get -1. 1/3 times -1 is -1/3. And then -2 times -1 is +2. And at this point, sometimes it makes more sense to go ahead and finish off each parentheses. Other times it'll make more sense to distribute the negative. I don't care which you do. Just use your proper evaluation techniques. Use your proper arithmetic, your order of operations. All right, I went ahead and did each parentheses. 1/3 minus 2, so that's 1/3 minus 6/3 is -5/3. Then I copy down the minus sign. And then -1/3 plus 2, so that's -1/3 plus 6/3 is 5/3. And that's -10/3. All right, that is the signed area of the region between the graph of that function and the x-axis. Now, what we don't know is we got a negative signed area. Yeah, we know there's more underneath. We don't know if the whole thing's underneath or just more of it, but more of it. Now, let me show you how to do this on your calculating machine. All right, so let's see. Our function is t squared minus 2. So let's see. X squared minus 2. Let's graph that. Now we want to find the integral from -1 to 1. So we go to our calc function. Number 7 on this one is the integral of f of x dx. So I choose number 7. What's our lower limit of integration? So I put in, use the negative, not the minus, -1. What's our upper limit of integration? 1. And there we go. Is that -10/3? That's -10/3. Now, that is something that you are required to be able to do on the AP test. So they'll give you just the most horrible looking definite integral you've ever seen to work. And if you know how to use your calculator, you got it solved in 20 seconds. If you don't know how to use your calculator, you will not get the right answer. You'll have to guess. So be able to do this on your calculator. Now, don't cheat yourself and try to do all of your problems on the calculator. You've got to be able to work with paper and pencil. For me, for college, for the AP test. So do it on paper, pencil first. then check it with your calculator. Or if you're getting stuck, it's okay to do it on your calculator just to see what your answer is supposed to be. But if you let the paper and pencil go, you will regret it big time. All right? Yeah. Well, and neither are your college professors. Okay? And just simple things like they may require you to always answer in a fraction. And if you do it on your calculator and you always get decimals, I mean, duh, they're going to figure it out. Okay? All right, let's do another one. Number 22. All right, evaluate the definite integral. Check it on your calculator. Number 22. We have the integral from -8 to -1 of x minus x squared divided by 2 times the cube root of x. And it ought to be scary because we can't find the antiderivative of that function. So we're going to have to rewrite. And the first thing I'm going to do is remember what that integral sign is. The integral sign in our definition replaced the limit of a sum, didn't it? It replaced the limit and it replaced that sigma. With sums and with limits, we can factor constants out and set them in front of the sum sign, the sigma sign, or the limit notation. So we can take out a 1/2 and set it in front of the integral sign. So we've got 1/2 times the integral from -8 to -1 of. But we still have a problem. There is no quotient rule for integration, for antiderivatives, and there won't be. We got to divide it out. Now that cube root of x is the same thing as x to the 1/3, correct? So, well, I could think of it that way, but I'm going to do division. I'm not going to think of it as an x to the -1/3. I'm just going to divide. That's an x to the 1 divided by x to the 1/3. When you divide factors with the same base, subtract their exponents. So 1 minus 1/3 is 2/3. So that's an x to the 2/3. Minus, and now I've got to divide x squared by x to the 1/3. So again, subtract the exponents. 2 minus 1/3, or 6/3 minus 1/3. Dx. Now, the dx is getting ready to disappear when we use the fundamental theorem of calculus. Use the proper notation. Most of you guys are getting better, finally, after a semester, of using the proper notation. Use the proper notation. It's the grammar of math. If you never used punctuation or capital letters, you would fail every paper you ever wrote, right? Even if you said what you said was great. Well, that's going to happen to you in college. It may not be the first math professor you run into. If I was your professor in college, I'd eat you up on notation. Because you're in college, you shouldn't make those mistakes. Right now, you're in a college class. You shouldn't make those mistakes. All right, now we use the fundamental theorem of calculus. So we've got 1/2 times. So we're ready to move to the capital F of x evaluated from -8 to -1 stage. That's what we're ready to do. So we've got to find capital F. Okay? So for this, for the x to the 2/3, use your power rule for antiderivatives. So we add 1 to the exponent, 2/3 plus 1, 5/3. And then we divide our coefficient by 5/3. Now, what's easier than dividing by 5/3?
Flip it.
Multiplying by 3/5. So 3/5 x to the 5/3 minus, what's the antiderivative of x to the 5/3? 3/8 x to the 8/3, evaluated from -8 to -1. So we've done that step. Now we're ready to get the capital F of -1 minus capital F of -8. So now it's a substitution problem. We substitute the -1 first. So look, it gets wicked here. I've got 1/2 times, all right? And then everything I'm underlining in blue, that's capital F of B, capital F of -1. Everything I'm underlining in black is capital F of A, capital F of -8. And what's between those two parentheses? A minus sign. So make sure you do the substitution carefully and correctly. All right, everybody with me on the substitution? Now it's arithmetic. So we've got the 1/2 out in front, then a bracket. Now let's work on the first parentheses. So -1 to the 5/3. Well, that's like the cube root of -1, which is -1, to the 5th, which is also -1. So that's 3/5 times -1, -3/5. And then the -3/8 times -1 to the 8/3. Well, that's like the cube root of -1, which is -1, to the 8th, which is +1. So that's -3/8 times +1, -3/8. Close the parentheses, copy down the minus sign, go to the next parentheses. 3/5 times -8 to the 5/3. That's like the cube root of -8. What's the cube root of -8? -2, and then -2 to the 5th, -32. And I didn't multiply that with the 3/5 yet. That seemed like enough to do it once. Then another minus sign, 3/8. Then I got to figure out what -8 to the 8/3 is. So it's the cube root of -8, -2 to the 8th. Well, -2 to the 8th will be positive because it's to the 8th. And it turns out 2 to the 8th is 256. All right, so with me? So we've still got the 1/2 out in front. All right, -3/5 minus 3/8. You get a common denominator. You combine your numerators. You get -39/40. Feel free to use your calculator for that part. To get a fraction, not to turn it into a decimal. We don't ever turn them into decimals if we don't have to. Okay? So then we copy down the minus sign, then we work on the next parentheses. 3/5 times -32. Nothing divides out, that's just -96/5. -3/8 times 256. I can divide the 8 into the 256. When I simplify that, I get -96. Again, it's okay to use your calculator to work with the fractions. We've got the 1/2 out in front. This time I decided to just go ahead and distribute the negative because I can use my calculator for the rest of that as long as I'm keeping them as fractions. So, yeah, batteries helps. So negative 39/40 plus 96/5 plus 96 is, and you probably guessed it, 4,569/40. And we still got to take half of that. So 4,569/80 is our final answer. Yeah, I would have been off. My guess would have been 4,570/80. So kind of what you thought it might be. Yeah, you're going to get answers that make you cry. Exactly. All right, so can we do it on here? So let's see here. Let's do parentheses x minus x squared, close the parentheses, divided by parentheses 2. Now let's see. How do I get a cube? Is there a cube root on here? Uh, 4. Cube root of x. Close the parentheses on the cube root. Close the parentheses on the denominator. Is that enough parentheses? All right, graph that. All right, so then we go to the integral. Lower limit is -8. Upper limit is -1. I don't know if that's right. So it's 57.1125. You typed something in wrong. No, I don't. And so 4,569/80 turns out to be 57.1125. Sometimes the teacher has to act like they don't know things to get you to think. Jeez. Number 25. Now, we're still supposed to evaluate the definite integral. I'm going to cry a lot because I don't have any idea how to find the antiderivative of an absolute value sign. And neither do you. Now, after you cry, and after you've decided to skip it because skipping is going to get you in trouble, you got to figure out how to do this. What do absolute value signs do? They don't always make it positive. What if it's already positive? Then it does nothing. It changes the sign. What if it's already positive? But doesn't the absolute value sign sometimes do nothing? Yep. So you can ignore the absolute value sign, and you've got a shot at getting it right. Or you can, and you must be able to do this. This isn't that hard.
I knew that.
If the expression's positive, the absolute value signs can be left off. If the expression is negative, the absolute value signs do change its sign. So if the expression is negative, put a negative sign in front of the expression, and you can leave the absolute value signs off. That's right. So on the interval from 0 to 3, the expression x squared minus 4 is negative between 0 and 2. So between 0 and 2, I need to put a negative sign in front of the expression, and I don't need the absolute value signs anymore. But from 2 to 3, the x squared minus 4 is positive, so I can just flat out leave off the absolute value signs. Just substitute. Look, I know 2 is the place where it's going to change, right? Because x squared is 4, x equals plus or minus 2, negative 2 is not in the interval. 2 is where it changes. So you just test a number. Between 0 and 2, test 1. It's negative, so it's always negative between 0 and 2. Okay? Everybody with me on how I got that? Now we have to remember our properties of definite integrals. We can break up an interval into as many subintervals as we want, right? So we're going to make 0 to 3, we're going to break it up into 0 to 2 and 2 to 3 and add those together. So the integral from 0 to 3 of the absolute value of x squared minus 4 dx can be rewritten as the integral from 0 to 2, and then look what I did. I took the absolute value. It's negative, so I put a negative in front of the expression. Then I went ahead and distributed that negative to get negative x squared plus 4 dx plus the integral from 2 to 3 of x squared minus 4 dx. Now, from here, I'm in pretty good shape. It's going to be some work, but I'm in pretty good shape. I need to find the antiderivative. Only thing is, I got to do it for each integral instead of just one of them. So add 1 to the exponent, divide by the new exponent, so negative 1/3 x cubed. And then just remember, it's a power rule, but if you've got a constant and you're finding its antiderivative, it'll be that constant times x or times t, whatever the variable is. Evaluated from 0 to 2. And then for the other one, add 1 to the exponent, divide by the new exponent, so 1/3 x cubed. And then the antiderivative of negative 4 is negative 4x. This time from 2 to 3. So we're at the capital F of x. We're at this stage, right? Capital F of x, evaluated from a to b. We have to do it twice because we had two integrals. Now we're ready for the capital F of b minus capital F of a stage. So we substitute there. We substitute there. So the yellow becomes the yellow. That color becomes that color. Notice there's a plus sign between the two brackets. But there's minus signs between the parentheses inside the brackets. So that gives us the capital F of B minus capital F of A. That's what's in the yellow. That's what's in the whatever that color is. Looks blue up there, doesn't it? Blue. We'll call it blue. And keep going till you get 23/3. Awesome. Oven mitts. Book. I got the new calculator on my computer from Mr. Thaxton. It's a book by Tony La Russa about the last season that he managed, 2011. All right, everybody able to get 23 thirds?
Yeah.
Now, do not put off doing your homework. Do not. I don't care. You got to have 1 through 25 done when you walk in here tomorrow.